My name is Siavash, and I'm going to present Model Agnostic Meta-Learning for Fast Adaptation of Deep Networks, written by Chelsea Finn, Peter Abil, and Sergey Levin. What happened here? Okay, sorry about that. Okay. The overview of my talk is as follows. I will talk a little bit about one-shot learning and what is that. Then we will talk about meta-learning and about this particular algorithm in meta-learning, model agnostic meta-learning, and we see how we can apply that method on supervised learning and look at their experiments, and we again look at how we can apply this method on reinforcement learning and look at their experiments, and then we talk about their conclusions. So what is one-shot learning? Humans generally can learn very quickly and from very few examples. For example, if I show you these two characters and tell you one of them is 1 and the other one is 2, you can easily generalize this, and if I show you this one, you say it's 1 and this is 2, and even if there are changes in handwriting, you can easily generalize and say what character are these one. And if you see something which is not similar to any of them, you can say that too. So we want our models to be able to do that. So what are the approaches we can have to achieve this? One of them is transfer learning. Transfer learning is that we train on lots and lots of data, and we are hopeful that we have lower level features which are shared between these and have some idea about handwriting, and then we can fine tune on new examples. The other idea is meta learning, and like metadata, which means data about data, meta-learning means learning about learning. So our idea is to have some method to learn how to learn these new characters when we look at them. So what are meta-learning approaches? There are different approaches in meta-learning. One of them is memory-augmented neural networks. The other one is optimization as a model, and another one which we're going to discuss is model-agnostic meta-learning. I'm going to go over these two very quickly. So memory-augmented neural networks, the idea is that we use a recurrent neural network and we add a memory to that network. So for example, consider the character recognition again, and we know that we have 3 labels. So output of the network is 3 labels. And we show this to the network, and it just gives us a random guess at first. For example, says it's character number 2, and we say no, it was 1. And then we show another example to it, and it again guesses. And when we show something like this, because it has a memory, it uses its memory and says, oh, I have seen something similar to this before. So it tells us this is probably 1. And the same thing happens here. And when we show it some new character which has never been seen before, it looks at the memory and says it's not similar to any information it has on its memory. So it says it's character 3. So there are many more details, much more details in their paper if you look at it. But the idea is a recurrent neural network with external memory. Another idea for meta-learning is optimization as a model. Here they aim to have another neural network for learn as meta-learner, so we have 2 neural networks here. One of them is for our particular task, and the other one looks at the loss and the gradient of the parameters of this first one and learns how to update that. Again, this one is a very complicated paper, but you can take a look at it.
So the best thing there is that instead of applying gradient stuck as a gradient descent, they're applying this kind of method.
Yeah, actually this helps them to apply that. Now we're going to talk about this algorithm, model agnostic meta-learning. So the idea here is that we do not want to have an algorithm which is based on our model. We want an algorithm to work with any model, like in supervised learning, reinforcement learning with recurrent networks. And the intuition behind this algorithm is, again, we kind of assume that there are some shared internal representations between the tasks. For example, we all have some ideas about what is handwriting. So those are shared representations, and we can transfer among those tasks. And it's kind of similar to transfer learning. In transfer learning, we say we want to learn our starting parameter, which trained on lots of data because they have good lower level features, and we can fine tune from them, and we hopefully have good parameters for that particular task. Here we we want to have good starting parameters which are sensitive to small changes, and also they give us large improvement on loss function for our particular task. So now I'm going to talk about a little bit about the notations we're going to use. We have a model F parameterized by some parameters theta, and our goal is to get an input X and output some action or label as A. And we have a distribution of tasks, and here we use a kind of more general notation because we want to cover reinforcement learning and supervised learning. So X1, A1 is this is the trajectory, X1, A1 from time step 1 to time step capital H, and this is our loss function. This is our prior distribution, and this is the probability of going to a state xt plus 1 if we perform action AT at a state xt. And this capital H is actually episode length. It tells us how many steps are we going to look at. So in supervised learning, we can simply assume that we just have one input and one label for that input. So there is no trajectory in supervised learning. And we define k-shot learning, just like one-shot learning, in which we just saw one character and we want to learn that concept. Here we just see k examples from one new concept, and we want our model to learn that. Okay, now let's look at our method. So if we have a particular task Ti and we have good starting parameters theta, then we can apply this gradient descent on starting from this theta and perform this, and we achieve this theta prime I, which is good parameters for this specific task. So for any particular task, we just perform one step of gradient descent. But here, for simplicity of notation, we just work with one step of gradient descent, but we can use as many steps as possible. So we can extend this easily. So what is our objective? So our objective, as we said, we want to learn our initial parameters theta. So we want to find initial parameters theta, which gives us the minimum loss on all of tasks when we adapt our parameters to be good for that particular task. So for task theta prime I, we adapt our parameters to that task, and we want our loss function to be minimized after we adapted our parameter. And that's for all the tasks. So we want this loss function to be minimized. And if we so this F is parameterized by our adapting parameters, and we want to find the minimum for that.
So maybe say a little bit more. Can you go the first equation, the top one?
Yeah.
So you're saying that we come in, the model is a little trained in that as theta parameter. And that's the theta, is that right?
Yeah.
And then we take task I,
yeah.
and we say take an example of that and find the loss.
Yeah. So if we have
find the gradient of that, and then update with that gradient from the previous data, and that becomes theta prime I. Right?
Yeah.
That's the way it's working.
Yeah.
So that's
yeah. So yeah, when we have these starting parameters, then we can just update for any particular task based on the loss of that particular task and performing gradient descent.
Yeah, because the network is a little trained,
yeah.
and current parameter theta, you put in the sample
yeah.
for that I task and give you some output, and you look at the loss.
Yeah, exactly.
And then you want to do the backpropagation on that.
Yeah.
Take a gradient of that loss.
Yeah.
And then with that you want to take.
Yeah. Yeah, but the problem, again, for our objective, we want to learn that theta. So now we're going to talk about how we learn that theta. So when the theta should minimize this thing for us, this term. And this term is nothing but the sum of the loss for all the tasks when we adapt our parameters to that particular task. So we want to minimize this, and this gives us hopefully a good theta, and then we can adapt to any particular task we want. Does that make sense? So this also gives us a better intuition about what this algorithm does. So suppose that our theta parameters are now at here, and we have 3 different tasks, task 1, task 2, task 3, and these are the best parameters for these 3 different tasks. And our parameters are right now here. And if we take derivative with respect to task 1, our parameters will be updated, and perform gradient descent, our parameters will be updated to here. Okay, and the same thing is for task 2 and for task 3. But through meta training, we eventually learn our theta to be here, and then from there, if we take derivative with respect to any task, we can quickly adapt to all of them easily. So this is our algorithm, model agnostic meta learning. This is just a general algorithm. So we have a distribution over our tasks, and we have 2 step size hyperparameters. We randomly initialize theta at first. So while not done do, we sample a batch of tasks, and then for all those tasks, we evaluate this term. This term is just the gradient with respect to the loss for that with just k examples. So we look at those k examples, and we evaluate this term, and then we perform gradient descent and update our parameters for that particular task. So this is theta prime I, which is should be good parameters for that particular task. And we keep track of all of these theta prime i's for all our tasks. And then we just do what we discussed in previous slide. So we want to minimize this loss. So we use these theta prime i's here to calculate this and perform gradient descent on that loss. And that's the end of the algorithm. Now we're going to see how we can apply this on supervised learning. So in supervised learning, we have regression, and the loss function for regression is defined as mean squared error most of the time. So this is the output of our network, and this is the label, and we want their distance to be as close as possible. And we also have classification, and we can use cross entropy loss. So the only difference which these 2 makes to our algorithm is just the loss function, but you can see the whole algorithm is the same. So here's the algorithm if we want to apply it on supervised learning. Again, we have a distribution over task, and we have 2 step size hyperparameters. We randomly initialize theta, and while not done do, we sample a batch of tasks, and for all those tasks, we sample k data points, xj and yj. So these are, for example, 5 examples of a particular class, for example, of a character. And we sample those data points for that task, and we evaluate our adapting parameters. So if we perform gradient descent based on these data, our adapting parameters will be theta prime I. So if we use these data points to evaluate our theta prime I, we kind of biased because we use them to perform gradient descent. So we also create something like validation data set, which is another examples of the same class. And we keep track of these data points and these theta primes. And then again, we update our parameters based on our validation data points based on this formula. And you can see this is the same algorithm, and for loss, we just can use mean squared error or cross entropy. There is no difference. So you can apply this algorithm on any supervised learning easily. Now we're going to discuss some of the regression experiments. So these sine wave experiments, we have 700,000 different sine waves sampled from an amplitude between 0.1 and 5 and a phase between 0 and pi. And we sampled k data points from interval between -5 to +5. So in other words, we have these sine waves, like 700,000 sine waves, and then we pick up k data points from each of them and we use them in our algorithm, and we learn those parameters theta after applying model agnostic meta learning. So we learn those parameters theta from here, and our model here is just takes as input the x and has to output the y value with respect to which sine wave we are using, and also it's just two fully connected layers with ReLU activation and 40 neurons in each layer. Now during meta testing, we have just one particular sine wave, and we just have k samples from that sine wave. So for example, I just give you these 5 samples from this sine wave, and then we use that gradient descent which we discussed to adapt our parameter to this specific test. So these parameters should give us a good approximate of this sine wave, but not just for these 5 data points, for all those points. So for evaluation, we pick up 600 data points from -5 to 5. We divide it to 600 points, and then we use them to evaluate how well our model works on these 600 points and calculate the mean squared error. They also compare with some baselines. One of them is pre-trained model, so it also pre-trained on all of those 700,000 sine waves, and but it fine-tunes on the sine wave for meta-testing that I showed you. And it's also again evaluated on 600 data points. And we also have an oracle, because we know the amplitude and phase of the sine wave, so we know exactly how it should look like. So here are the results. When we use k equal 5, this is the plot. So this red one is the oracle, which is the sine wave which we had to adapt to. And this lighter green is our parameters theta before adapting to this particular red sine wave. So this is our initial state. And then these 5 data points are the data points which we use to adapt to this red sine wave. And after adapting, we end up with this theta prime, which is this darker green color and you can see it kind of overlaps with our oracle and quickly adapts to that sine wave. But when we use pre-trained model, here again the red is our oracle, and this lighter blue is our theta. And again we use the same data points and we apply 10 steps of gradient descent, but our theta prime is not that good. And then again we have 10 data points, and this is the same thing you can see, and this is for pre-trained model. So these are the results that you can see. We have mean squared error here, and we have number of gradient steps here. So after applying one gradient step, you can see that mammal quickly adapts to the oracle, and then it kind of works very better than pre-trained model. So now we're going to talk about classification examples. We have n-way classification, so it means that we use n different class with k-shot learning. And the network architecture has 4 modules of 3x3 convolution and 64 filters at each layer, and a ReLU nonlinearity and 2x2 max pooling. Also, we talked about memory augmented neural networks, and because they wanted to compare with them, they also had an architecture which does not have any convolution, so to be fair. And that's just a 256, 128, and 6464, and they have ReLU activations. It's fully connected network. So what are the benchmarks for classification? One of them is OmniGloat, which is a data set of 1623 characters from 50 different alphabets. And each of those characters has 20 instances, each drawn by a different person. And for training, we use 1,200 characters. And for testing, we pick up 5, or because it's n-way classification, we pick n from these 423 characters. Another benchmark is mini ImageNet. So it's some images of ImageNet, but it's smaller, so it just has 100 classes, and they use 80 for training and 20 for test. So I'm going to talk, in the results, they show the results for first order approximation. So what's that? First order approximation, in our updated step, we just update theta based on this rule, yeah? So here we have to take derivative of this term. And this term has theta prime I in it, which is also take derivative of this term. So we have to take second derivative from this, our parameters. So instead of doing that, they just use first order approximation of that second order derivation. And these are the results. So this man is a memory augmented neural network, and this is our algorithm with no convolution. These are state of the arts, and this is ours. And we have 5-way accuracy, which uses n, as we said, n-way accuracy was using n classes for testing. And one shot, we just see one example of each class. And these are the accuracy, and you can see that model agnostic meta-learning performs very well. And 5-shot, here is the results for 5-shot. And then again, they do 20-way accuracy. So we have 20 classes, and we want to see how well we can adapt to those by just looking at one example or looking at 5 examples. And this is the same thing for mini ImageNet. So they just do 5-way accuracy with one shot. And here are the results, and this is for 5-shot. And now we're going to talk about the reinforcement learning. In reinforcement learning, the loss function is actually our negative of our reward. So at each state, we perform an action, and we get a reward for that. And if we sum all of them in our trajectory, then it gives us a reward for that. So the algorithm, I wanted just to show you that it's still the same thing. We have a distribution of our task, and we have alpha and beta, and we have initialize theta, and sample a batch of tasks. And for all tasks, we sample k trajectories. So the only difference here is that we pick up k trajectories. And we evaluate again our adapted parameters based on those trajectories. And we also have a validation data set, which are trajectories which should do well on these adapted parameters. And then we again update our parameters based on our validation data set trajectories. So the experiment in the reinforcement learning is 2D navigation. We have a point agent which must move to different goal positions, and target is randomly chosen from a unit square, and the agent should be within 0.01 of the goal, and that's a success. But after 100 steps, if it cannot achieve there, then it's a failure. And they use 100 iterations of batches of size 20, and the reward is the negative distance to goal. And our episode horizon limit is 100, the thing which I just said, that after 100 steps, if it cannot achieve to goal, then that's just a failure. And they use 40 trajectories for their test. So now let's talk a little bit about what algorithm they use in their reinforcement learning problem. So we have a point agent here, and these targets change. So we want our parameters to, and this is our network. The input is just the x and y coordinates of the agents. And then we want our network to tell us what action to perform. It gives us a probability of all the possible actions. And then we want to be able to adapt quickly to different goal positions. So one algorithm for reinforcement learning is vanilla policy gradient. So in that, we randomly initialize our theta parameters of our network. Then we perform k rollouts. So what is a rollout? A rollout is just we give the current state, the current coordinates of our agent to the network, and then it gives us a probability over different actions. Then we sample from that probability. So then we sample from that probability, and we perform the one action based on our sampling, and then we go to a new state, and we again do the same thing. And we end up with some kind of trajectory. So this is, for example, the output of one rollout. We do k different rollouts, and our agent performs differently in that environment. And after the rollout is done, we can see what is our reward. So for example, here we are very far from the goal. So probably that wasn't a good trajectory to take. And then we update our weights based on that, based on the reward from those trajectories which we sampled, and based on the collected rewards, and we repeat this thing. So we repeat, and we probably end up with better rollouts, and we learn to do good rollouts again, and not to do bad rollouts. And eventually our agent learns to move toward the goal. So here's our experiments on reinforcement learning, and you can see these are the pre-trained, so without performing any adaptation to this target position. And this is the pre-trained model, not model agnostic meta learning. And after 3 gradient steps, our policy or footprints of the agent become something like this, which is kind of noisy with respect to model agnostic meta learning. So eventually our theta parameters are here, but after 3 steps of gradient descent, we can have very good parameters for this specific task. And this is also the same thing for reinforcement learning. You can see after performing gradient descent steps, model agnostic meta learning very quickly adapts to the oracle. Another experiment of reinforcement learning was locomotion. We have 2 different simulated robots by Mojoko. One of them is planar cheetah, and the other one is the 3D ant. And the goal is to run in particular direction or run with a particular speed, and these are the agents. And these are some videos of those. So this is randomly initializing our policy and then performing 1 gradient step on 40 different trajectories. And there are 2 different tasks. One of them is backward task, the other one is the forward task. And this is the model agnostic meta learning. So this is our theta without performing any gradient descent. But after 1 gradient descent, it can adapt very good to backward task and to forward task as well. And if you perform more gradient steps, it performs better. And this is the same thing, but here the goal is to move with a particular speed, move forward with a particular speed. And here goal velocity is 0, and it's 2, and it's just perform 1 gradient step. And these are pre-trained, so this is not model agnostic meta learning. And you can see it cannot kind of adapt quickly. But here is the result for the same task, but for model agnostic meta learning. So if we start from that policy and perform gradient descent, the agent quickly adapts to that task. So as conclusions, model agnostic meta learning is applicable on many different methods. You can use it on recurrent networks or convolutional or whatever you have. And any method actually has some parameters and a smooth loss function. You can apply this algorithm on it. And even you can adapt if you have many amount of data. It's not necessarily that you should it works just with a small amount of data, and because it's just gradient descent, yeah? So you can perform as many steps as you want. And in future research, they talk about multitask initialization, and actually this is a paper in 2018 they published about this. If you want, you can take a look at it. And that's all about my presentation.